We will conclude this lengthy introduction with the extreme value theorem. Which will probably not be used a whole lot throughout the rest of the text, mostly in this section, because it's concerned with finding absolute extrema, and throughout the rest of the chapter, it's more concerned with relative extrema. Sometimes relative extrema are also absolute. That's certainly possible. I mean, they can be both at the same time. One's not preclusive of the other. Extreme value theorem is if f of x is continuous on closed interval AB, so a very small requirement, just continuity over a closed interval. If f of x is continuous on AB, then f of x has both an absolute max and absolute min on that same interval. I'm just going to give a pictorial representation to demonstrate this. So minimum on the same closed interval AB. We'll have both. You could also have relative. Again, relative extrema can coincide with absolute extrema. That's not a problem. As a matter of fact, very often happens in these types of extreme value theorem problems that they are one and the same. Let me just draw a very simple picture here. I'll show what I mean. Here's x and f of x. Let's draw something like I've drawn before. Maybe something like this. Okay. So this is a continuous function, surely. And now if I take any closed interval, so I've been drawing open intervals when we're talking about the relative extrema, because that's their definition, defined over open intervals. Now you have closed intervals, so this changes the game entirely. So let's just draw something here, and something further over here, maybe, I don't know, something like that. All right, so this maps up to a set of function values. I'm going to draw them in red again, like I've done before. And I'm going to draw a closed interval looking object here. And so too over here. All right, so we're thinking about this set of function values, this subset of the range of this function. Okay. And the claim of the extreme value theorem is that because we're using a closed interval specifically, there must be an absolute max and absolute min on this closed interval. Okay, so let's find it visually. Absolute min, well, that's pretty obvious. It's right down here at this trough, right? It's a relative extrema, or extremum. It's a relative extremum for the whole function, right? Because it's only happening locally here for the whole thing. So this is a relative extremum for f of x altogether. But when I'm looking at this closed interval here, it is an absolute minimum on the closed interval. Okay. Absolute min on A and B. Sorry, I forgot to label A and B. A and B there. Okay. So we have an absolute min on AB, clearly. It's that trough. So again, here, a relative extremum was coinciding with being an absolute extremum as long as I'm looking at this closed interval. All right, so now where is the absolute maximum according to the extreme value theorem on this interval? Well, I can now safely look at the endpoints, because they are now included, because I'm using inclusive notation here, I'm using a closed interval, so therefore the endpoints of this set of function values are also included in this set, and I can now select the highest value here because it is part of that set, right? So there's our absolute max over there at the endpoint. And in these types of problems, that is often where one of the absolute extrema will be located. It will be at the endpoints. So I have an absolute maximum, again, on closed interval AB. if I were looking globally at the whole function, it has no absolute max or absolute min at all because it continues to infinity here and to negative infinity here. But once I start looking at some closed interval of a continuous function, I am guaranteed to find an absolute max and an absolute min within that interval. All right? So since we see that it happened either at an endpoint or at a critical value, it turns out those are the only places you have to look when dealing with the extreme value theorem.